Am I audible, sir?
Yes, sir. Yes, sir. You're audible, sir. You're audible, sir. Just 2 minutes, sir. We'll start the session, sir.
మీ దగ్గర ఉంది కదా ఫైల్ అయితే యూట్యూబ్ లింక్ అయితే
ప్రణవ్ సార్ వచ్చిన కదా
వస్తున్నాను
మనం స్టార్ట్ చేద్దామా?
వచ్చి
ఒకసారి ఫోన్ చెప్పండి సార్. ఫోన్ సార్ రెడీ అని ప్రణవ్ సార్.
స్టార్ట్ చేసిరా లింక్ ఎవరికి ఇచ్చారు?
అందరికి ఇచ్చిన
వాట్సాప్ చేసిరా అందరికి? సార్ స్టార్ట్ చేసేయండి. సరే మీరు స్టార్ట్
మీటింగ్లో నేను చెప్తాను చెప్పు.
ల్యాప్టాప్ కనెక్ట్ కాకుండా
Good morning to all the participants. So we'll begin the session in 2 minutes.
ఇప్పుడు పెట్టినా మళ్ళీ అన్ని గ్రూప్స్ మీటింగ్ లింక్ యూట్యూబ్
నేను ఫార్వర్డ్ మళ్ళీ ఫార్వర్డ్
పెట్టినా చెప్పిన వాళ్ళ మళ్ళీ పెట్టాలి.
Welcome to all the participants on the day 2 of the 5-day workshop on the innovative methods in the finite element analysis of ABAQUS and ANSYS. So we'll start our we'll start our session today. I would like now to request the Pranav sir to introduce our resource persons today. Pranav sir.
Yes, sir. I'm here, sir.
Go ahead.
Am I audible to you, sir?
Yes, sir.
Yes. Good morning, everyone. Welcome to the second day of the one-week national level workshop on innovative methods in finite element analysis using ANSYS and ABAQUS. Today's first session is on finite element applications in metal forming by Dr. J. Kandaswamy, Professor, Department of Mechanical Engineering, MVSR Engineering College. Dr. Kandaswamy completed his bachelor's in mechanical engineering from the University of Madras before going on to finish his master's and his doctorate from JNTU Hyderabad. An eminent researcher and faculty, he has over 20 years of experience in teaching and has over 70 publications in various and reputed international journals and conferences. A lifetime member of the Indian Institute of Welding, he also acts as a reviewer for the Institute of Engineers Journal D and the International Conference on Innovations in Mechanical Engineering Skills. Dr. Kandaswamy has also completed and is working on research projects on the tune of over 20 lakhs approved by ASCT, UGC and IEA. On behalf of the Automobile Engineering Department, I would like to thank Dr. Kandaswamy for sparing his valuable time in giving us this presentation. I please welcome sir to take over now and please begin his presentation.
Am I audible, sir? And whether my screen is visible?
Yes, sir. Your screen is visible and you're audible, sir.
The participants. Dear participants, if there is any technical glitch in between, do Vijay can call me because I may not be in a position to see the screen
Sure, sir. Sure, sir.
of this type. So that's the reason
Yes, sir.
I request you to. Right.
Do. Thank you, sir. Okay.
Okay. Yeah. Is the screen visible, sir?
Yes, sir. Yes, sir. It is
Fine.
visible, sir.
Right.
Yes, sir.
Okay. Pleasant good morning to the participants who are very much interested in joining this 1 week national level workshop on innovative methods in finite element analysis using ANSYS and ABAQUS. Myself, Dr. J. Kandaswamy. Thank you, Pranav, for that words. And let me go into the topic slowly. Finite element applications in metal forming. Of course, finite element is a tool. It's like a mathematical tool that can be applied to any field of engineering, right? And I have used this tool, particularly my team and my students, and we has used this tool for metal forming applications. Of course, what is the need for this particular finite element applications or finite element analysis, finite element methods, finite element techniques, however you call it as? See, normally we might have heard about Einstein's theory, Avogadro's theory, Newton's theory, many theories that you could see on the left hand side of this screen, which has a lot of derivation, mathematical formulation, this, that, and at the end of the day, you will end up with an equation called either E is equal to mc square or V is equal to U plus AT, or all these formulations come with a set of assumptions. This theory comes with a lot and set of assumptions. Any theory has many assumptions, and then only we will go for. Otherwise, we can't solve the problem actually on paper. So whatever results you get, exact answers 9.7864, like that we used to say answers. All those answers are far beyond real life situation. Maybe on this end or that end, whatever it is. Theory gives only a bird's eye view of the phenomena, but may not be the real life situation. Fine, very nice. But whereas when we conduct experiments, which is happening on the launching of a rocket or crash analysis of a vehicle, right, or impact test, whatever we do of a bullet, all our experiments which where the results are real, exact, success, failure, no improvement, like that, many will be there. So experiments are costly and time consuming. So see, the left hand side is with a set of assumptions, and I am not with the real life situation, whereas the real life situation is costly and time consuming, but results are nice. So how can I bridge the gap? How can I strike a deal between this theory and experiments? There are many methods that have come up, but in 1950s or 1956, framework method was presented. This framework method initially for civil engineering applications, it was started, and that bridges what? Finite element analysis. You could see the connecting rod which connects the piston and the cylinder, right? Or else how the energy is transmitted. The same way, how from theory to experiments, how I can bridge the gap in between so near and so far, like that. That way, I could use this finite element analysis for anything. And after 1950s, the evolution of computers and the computing power, change in computer arena totally are very interesting. So that's the reason why finite element analysis have picked up. If you see, the number of papers that has been published has been exponentially grown on this particular finite element analysis in open Indian literature, right? So finite element analysis is a tool, it's a technique, it's a method which uses lot of max. Any student, if he has passion for matrices, max, calculation, then naturally this particular method will invite him with love and affection. That's the beauty of finite element analysis. You could see a number of figures, colorful pictures, all these things are possible only with finite element analysis. If you see here, I can't do something in real life experiment, but I can do it in finite element analysis. I can stop in slow motion, I can stop and see what happens. All those things may not be possible in a crash analysis of a car. Every moment I can take back, reverse back, go and hit. Once again I can come and hit. What not I can play. It is like a toy for me. I can make computer and the system as a toy and I can play. Finite element analysis is a tool, it is a technique, it is a method. That's what first one should understand. It's a very powerful tool. It's a very powerful tool. Right. Okay. So all this might have been presented yesterday, or so I may not. I'm not aware of the contents that have been covered yesterday. But still, as my part is into manufacturing, everywhere you could see it is a numerical method used for solving problems that cannot be solved analytically because of geometry, different materials, different boundary conditions, different problems that arise in real life situation. You could see over here, it's a very simple rolling process. This is before rolling and this is after rolling, and we do lot of max calculations, sine theta, cos theta, tan theta, inverse, cosine, all those Fourier series we apply, logarithmic evolutions we use, and at the end of the day we try to find out some stresses, strain, displacement, residual stresses, or my outcomes, what will happen after that if I change the input. This is the basic idea. So then the same thing can be solved. This is analytical formulation or theoretical formulation with pure max. So later this may give you results, exact results, but is not that which will not come near to the real life situation. So then this is what your finite element analysis is, where the same rolling can be analyzed using what? Finite element techniques. So this shows you a 3D analysis and this shows you a 2D analysis based on the computational power you have, the RAM capacity, like in colloquial language of engineers, computer engineers, the RAM capacity that could solve the matrices in seconds. How many, what is its RAM capacity? Based on that you can go with 3D analysis or you can go with 2D analysis. Only thing you should know, it suits very good computers because hand calculations, it's painstaking. So originally applied to problems in solid mechanics. Naturally it started with structural mechanics like beam problems, like analysis of beams, like that they all started. Then slowly it has percolated into all forms: heat transfer, fluid flow, manufacturing, electromagnetism, combined phenomena, all those things. To use this tool, either you call it as ANSYS, either you call it as ABAQUS, either you call it as COMSOL, either you call it as LS Dyna, MSc Mark. In the market, number of you say your domain, they will give you the software. So now any student or any scholar or any person who's intended to work in FEA should have the knowledge of domain. Without domain knowledge, without knowing rolling direction, without knowing neutral planes, without knowing slip, I can't go and solve anything in ANSYS. So students, one should have domain knowledge and have passion for maths and then have patience to sit on computer. Then naturally you can, this is clay, child's clay. You can play with it however you want. You should have the passion for the subject and patience for sitting with the computer. Then things will be very nice, very nice. So this is how we go ahead with. So these are the phases of finite element method. Pre-processing, that's what mathematical model you have first, then you discretize it, we will see what is everything, and then you have an FEA model, and then you solve it. These are the three phases of any finite element analysis you apply for any domain: structural domain, heat transfer domain, vibration domain, wherever you want, electromagnetic domains or manufacturing domain, wherever you want, you can apply. But these won't change. These won't change. Pre-processing, solution, post-processing. So pre-processing is like giving inputs. What is the you have to model the geometry, and then you have to apply material properties, then you have to mesh, then give the boundary conditions, initial conditions, all, and then say solve. Then the matrices are solved in this based on the type of whatever inputs you have given, and you can extract post-processing colorful results. What you see over here like this, you can extract various results and analyze, and you can understand. Then I call it as, these are the three basic steps of finite element methods, right? So what are they? One is pre-processing, another one is solution, and another one is post-processing. So what are the inputs you are going to give? It will be geometry, it will be modeling the geometry, understanding the material properties and application of material properties, meshing, and then this meshing is what called discretization, we call it as, and then the applying the boundary conditions, right? So the same way, the solution depends on the computer accuracy. The finite element discretized model, which is approximated to numerical solution, you can get only approximate solution in FEA. You can never get the real exact solution as you get in experiments, or else you get in what? With hand calculation using analytical analysis for a given set of conditions, right? So FEA can only give you approximate results, right? So this is what a discretization procedure. First, students, I should have my domain knowledge. Whatever you read, you should know first what is displacement. From displacement, I can calculate strain. From strain, I can calculate stress. From stress, I can calculate reactions. From reactions, I can calculate strain energy, and it goes on like this. That is how one should have the knowledge of domain. Without domain knowledge, we can never enjoy, right? So continuous, what is discretization is all about. First I will show you this. So this is what a domain is. Domain knowledge. This is domain knowledge. If I give you a problem like this, you can't eat it like this and say what is the taste of this particular fruit. So then you have to eat pulp by pulp, right? So that's what is over here. This is what called as the process of domain, problem, and then this is discretization, right? Anyway, like this is your domain, this is your problem, and then you have discretized over here what is every element. You eat every element, you solve every individual element, and then you see what are the results, what are the outcomes, and then you say, you come like this and you go back like this, right? So this is what your discretization is. Anything that is having infinite degree of freedom, this particular problem will have infinite degrees of freedom, but here you have finite degrees of freedom. You can calculate the number of degrees based on the elements. This individual entity is called element, and the connecting points are called nodes, and the connecting points are called nodes. So that's how now you could see this. So this is having infinite degrees of freedom, and this will have converted into a domain with finite degrees of freedom. So continuous elastic structure divided into small but finite, well-defined substructures called elements. Elements are connected together at nodes, nodes having degrees of freedom. So discretization process is also known as meshing. So how better you mesh, that better you will get results. But more you mesh, the computing time will be more. So you have to strike a balance. It's all come by experience. You have to keep on see any tool, any FEA tool, you call it as ANSYS. It's not Greek and Latin. It's not rocket science, students. One day you start, down the line you will be an expert. Down the line you will be an expert. Point is how better. It's like learning swimming. How much time you spend in your swimming pool, how much time you spend with your computer, with that particular software, with particular domain. That's how you gain your experience. So you have a set of library and all these elements. That's what every pulp I told you, no, every element, maybe a 1D element, maybe 2D element. 2D I have two different types: plane strain condition, plane stress condition. And 3D I have different types of elements. Based on the geometric model, I have to use the element and mesh it. So it's not only, so this is how I make pre-processing and all. So this is all about pre-processing. I will give input data like raw material data. I select the element and then I discretize and then I go for what a formulation of the matrices and then I say solve, and it takes time to solve in the meantime, and then I will get results. So pre-processing, solving, post-processing. Not necessary this FEA has grown today. It can be used in what medical sector also. You could see for all bones are considered as structural elements of this particular human body, and all are analyzed. A mechanical engineer or an automobile engineer or any engineer can involve himself in medicine field also through this particular usage of what finite element tools. So you solve it. You runtime proportional to nodes or elements. Matrix operation used to determine unknown degrees of freedom. Basically, you try to find the field variable. The field variable in a displacement problem is in a structural field is structural domain is displacement. In a heat transfer domain is temperature. In a flow domain is velocity, and it goes on like this, right? So that's how. So now I go into my, so giving this of pre-processing, solving, post-processing, I go into the concept of my forming knowledge, right? So what is, so now the participant should be aware that one should have first the domain knowledge. One should have the domain knowledge for creating the mathematical model, and then he should discretize, and then he will create his FE model, and then he will solve, and then he will take results. So this is input, this is output, and this is solution of matrices, purely max, right? Now, what is happening behind ANSYS? What is happening behind ABAQUS? So, all this are a set of equations, max being solved. So, first is formability analysis of AA7075 by superplastic forming of conical shaped components. So, this is the application. I should come always from where I use, why I use, how I use, all these things I should know, right? And at what sort of environment, what will be the temperature, what will be the working environment, what will be the speed, feed, everything I should be, that's what called as domain knowledge. So now I want to manufacture like this. So then if at all I have to manufacture, how can I do it? What will be the strains? How much input I can give in experiment to get this thickness, how much pressure I can give, for how much time I have to give, how can I give, whether in steps or continuously or Can I given step hold it, or continuously and I have to hold it? So all such domain knowledge I should have first, right? Next is, so these are basics. So what is elasticity, what is plasticity, and what is super plasticity? So I will show you this to understand super plasticity. I have one beautiful yeah, this is what super plasticity is. How beyond you can blow off, how a material like a titanium alloy, a material like aluminum alloy, a material like magnesium alloy, how beyond I can blow, so that it will be so thin my payload will come down, right? This is used in aircrafts and all, like in aerospace application. So it should be very thin, but its stiffness should be very high. Stiffness should be very high, but it should be very thin. So like the difference between your ambassador car door and Kia door car, how to close an ambassador door car you require one person with full force. A small child can go and close a Kia motor car's door. So that's the difference. You want strength, but stiffness should be very high, but thickness should be very less, very less. So then how can I achieve those what do you call two different ends? Two different ends, how can I achieve that? So then I go with, you know what is elasticity? It is the property of a solid material by virtue of which it tends to regain its shape after the removal of. And plasticity, we are going to see plasticity in this zone only. This is our zone, plasticity, and beyond it is what called as super plasticity, where how the grains slide, and I could get that very, what do you call, nice very fine thinness. It should be thin, it should be very thin, but stiffness should be very high. So that's how, for getting that super plastic, I have to severe plastically, I have to deform it. And every material gains this nature, like some person will get tensed when he sees something, when he listens something, like that. Any material you heat up to a certain temperature, in that certain temperature range it tries to go beyond extension. Ductility will be very high, unique ductility, right? It can keep on going. You can make it that much ductile, so that you could see the deformation rate is more, deformation rate is more. So these are some examples of some SPD techniques, so that how I can balance between my strength and stiffness of any material. I can use high pressure torsion, multi-axial forging, twist extrusion, equal channel angular extrusion. I have one case study on this also, right? This I have one or two. So super plastic forming, so cumulative roll bonding, constrained groove pressing. So all this are various super plastic forming techniques. So like any domain, this domain also have lot of max into that. This is not the time so that we can discuss max, and all the participants will simply switch off their audios and mics and just go on. So not so like that. That's why I kept so lot of figures, so that you can enjoy this session, right? So we have lot of, for every particular process over here, lot of max knowledge is required, domain knowledge is required, right? And this is what super plasticity is. So what is super plastic forming? Any sheet, so capability of some material to undergo large uniform elongation prior to necking and fracture tension. So that's what I will do that. So now what I'm going to do is, this is what now I am going to do. I will apply pressurized forming gas, an inert gas, right? Carbon dioxide, anything like which won't react with the environment. You have to apply argon. Argon is cheap, available in the market, so that you have to apply. And this is the die shape. You blow it, it has to form, but the condition is thickness should be uniform. You see the thickness of this formed component, it should be uniform. It should not be very thin at one point and very thick at another point. That's the beauty of this particular plastic forming. right? So then there are a lot of max you can enjoy. So where and all I can use, you should understand, really this fellow is talking this many things, is it really used? You should see very light in weight, but you have what stiffness is more means, then actually it is super plastically formed, or else it should have undergone the severe plastic deformation. Then only you can gain that strength balance of, you can strike a balance between strength and stiffness, right? So all this you can, it can be used in dental applications, maxofacial applications, all those things, like a titanium alloy which is very light in weight, it won't harm our body when suited, but forming is a Herculean task. Forming becomes a very tough task. It's not so easy to make this. Aluminium you can easily form, steel you can easily form, but not the titanium alloys, right? So like that you can use for domestic application, you can use for structural application, aerospace applications, all many applications you can use wherever payload is of important, like an for any automobile engineer the payload is of the. So what we have tried to do, so this is how we do. We have we select the material, you can see over here all three will come over here. You have geometrical calculations, you have numerical analysis, you have experimental investigations. So do calculations from analytical, and then you go with what these results will never match with this, and so that you do FEA, and then you can see you go very near to that. So that's how you have to select the material. Material knowledge is very important, because without the selection of the material is for any project, if I say I'm going to build a bicycle out of gold, then cost is different. Of steel, cost is different. Selection of the material decides 50% of the project cost. 50% of the project cost. So hence, one should understand the importance of materials. So then I will manufacture a die like this. Okay. So for that, that's what I say. First, you should create your 2D drawing, and then you should create your solid model. You should have your manufacturing components, and then you should go for analysis. So that's how geometric approach, or else gaining domain knowledge with all these things. Lot of max I have to use, and that's what I told. All basics max of 7th class will help us a lot. So students enjoy learning 7th class, right? Max. Then that's how I do calculations and I take graph. This is my first part. Of course, you may not be interested in. Then comes the software part, what your FE part is. For this finite element analysis, you are using ANSYS and ABAQUS. Any tool will work on the same concept of finite element analysis, right? Then I use a constitutive equation of mark, and then this is as usual. I told what you will do, you will design the geometry and mesh the workpiece. That's what your pre-processing is, right? Then you apply boundary conditions on the workpiece. Which one is to be fixed? Which one has to move, right? Then you will say material property and geometric property. What are the property for die material? What are the property for sheet material? How the contact is going to be? That is contact analysis. Contact between the mesh body and the die. And then you have to run the load. See, as far as structural is concerned, or else what beam is concerned, like analysis of beams, analysis of columns, structures, or else solid mechanics, time won't come into picture. Whereas manufacturing, time comes into picture. For every delta t time, the particular mesh has to deform, remesh, and once again it should be ready for the next cycle, and then you apply the force. Then the mesh has to change, remesh, and it has to be ready. So that's how I go for, I submit the job and I will run the analysis. That's what called as solving the analysis. After solving, I will get post processing. Anything will be like this, same flow chart. You could see what pre-processing, you have a coordinate system, mesh generation, spacing, expand and rotational, all you could see. Step by step, you keep on growing this particular tree. How contact bodies behave, how the friction will be. That is a very challenging criteria in manufacturing analysis. You apply the boundary conditions, you apply material and geometric properties, which are deformable bodies, which are rigid bodies, and then you say the load case analysis. What is your convergence when you say the problem is solved? As many of the time the solution won't converge, meaning you won't get results. The problem keeps on running for days and days and days, and you won't get results. Then it is of no use, no. So then that's why how to converge it and then save results and taking out. This is extracting the results. That's what called as post processing. That's how I do in MSc Mark, which is a Russian software we use for exclusive for this particular superplastic forming. So this is how I model in what? This is how I model in this is how I model in my MSc Mark, and then I go for meshing, right? So then these are the how I fix the boundary condition. You see the sheet is fixed at the corners, fixed along the circumference, and I apply face load, meaning pressure is applied on the sheet, right? And then I will go for what? I give geometric properties. What are the geometric properties for this particular sheet, for this die, everything. And then I have to give material properties. I have to give geometric properties, I have to give material properties, and then I will say simulate. So then you could see the mesh gets deformed every time, and whatever output you want, you could see, right? The displacement, if once displacement field variable is known, you could see. This is how we simulate. It is a 1 mm thick sheet. See, the die is hidden, it is not shown. Die is there. Don't think otherwise. You can't form. Right? So it keeps on slowly. Students, all these things won't come. For this, for getting this particular stage, a student has to continuously work for 6 working days a week, 6 months at least. Then he can reach this. For a beginner, later he will be. So that's what we form, and you could see how the meshing, it's remeshes every second, and it keeps on forming like this. So what you are seeing is how stresses are distributed into the sheet, right? You can see displacement, you can see reactions, all those things slowly, right? So it indicates this is very stressed zone slowly, and here and all, because naturally thinning will be more over here, right? So this is one application of what MSc Mark and FEAAA tool, a Russian software, which is being used for finite element analysis of sheet forming, right? So that, and then after forming, how it will be initial stage. Yeah, you could see over here, initial stage will be like this, and an intermediate stage, how the sheet is formed inside that, and what is the final stage, you could see over here. So this is how sheet is formed, right? So then you could play with the post processing. All these are generated by the software only. So then you can extract results whatever you want. Post processing, you say pressure versus time, how the thickness of that particular sheet, how the thickness of the particular sheet varies with time, or arc length, you could see. Yeah, this is another beautiful show that student will love to see. For quarter circle, how it forms. For half circle, how it forms. For 3/4, how it forms. For full simulation, how it will be. That is shown for different thickness. You see, for 0.5 mm thickness, for 1 mm, it's still forming. You could see over here. So for 1.5 mm sheet thick, how it will form. For 2 mm sheet thick, how it will form. You can see. That's what. If once you are set up with one model, one process, if you are successful, then you can play but experimentation is very costly, right? So this is the beauty of finite element analysis tool, right? So you can enjoy and you can create graphs, of course, and then comes all those things. But how far it is correct, you should check. No, validation is very important. Whatever you say may be colorful, but who will believe? Will you believe or I believe? No one believes unless you show in experimentation. So because this is what actually will happen at the end of the day, then I have to create all these models, and this is how I will roll the sheet. I will cut the specimen, and then I will keep the sheet in the die what I have had over there, and in the same die I will so that this is a different how much it is formed. You will form the same sheet over here, and then you will check with the thickness of this, how the thickness is varied with your finite element analysis. So it will be a very useful analysis. So that's how I can show you how I can change all these things, and how these you could see. And that's what I told. Analytical method is far beyond. Whereas you could see over here, it is overlapping here and there. Approximate results I can get with the FE simulation model. How the thickness of the component varies. Right. So this is as far as my first case study is concerned. This is for a cone. No. Now I did this for a cylinder. Now I did for what? Same cylinder, right? Same superplastic forming phenomena. That's what, student, we are not in this elastic zone. We have to go beyond this. After yielding, you should start working. So plastic region, you should work, right? That's what then you can see. So lot many things can be shown. Same way, you could see finite element analysis and conduct of experiments. For this, I have not used any analytical calculations. Then select your material properties, right? You have to go with what? You see, I'm going to form a cylinder. That's how I can reduce my cost. I remove, see, I can make a cup like this. Of 20 mm. If I remove this biscuit packet, it's like a biscuit packet. You remove the first biscuit, then I can make a cup of 20 mm thickness. If I remove the second biscuit, I can make a cup of 30 mm thickness. I remove the third biscuit, I can make a 40 mm cup. So I can go on increasing my with one die. That's how I think. Hello, am I audible to the? Yeah, right, fine. So this is how we go with forming all these things. So you have 3D model of cylindrical die and lid same way, and then you form all these things. You have to do some calculations as, yeah. Once again, same story. You have to generate the die. You have to generate the model. You have to apply boundary conditions. You have to give material properties, geometric properties, solve. Same in MSc mark. Input parameters I have given. We have solved. Yeah, you could see quarter case. It is axisymmetric. Initially, student will start with a 2D case. And he will start because computers will be very, very RAM capacity will be very slow. Whatever laptop we have, all conventional laptops will be of normal. For this, you have specific systems. So that's the beauty of this. You can see I have taken a quarter of an axisymmetric component, and then I have applied all the boundary conditions, and you could see how it forms for a 20 mm, how it forms for 30 mm, how it depth of form. That's what I told you. Now I'm going to create a cup. How the cup will get generated, you could see something. Okay, yeah, here you could see how it forms for a cylindrical die, and that's how experimentally I verify. Yeah, here it is forming. The water bubbles will come out, and based on that, whatever volume of gas is here, if you form, that comes out, that I will take over here and I can measure by back volume method. It's called as, right? So depth of form is only 20 mm. Yeah, you could see now 60 starts forming. 60 starts forming. Yeah, that's how cylindrically we will form. That might be a cone. Yeah, depth of form is 60. This is how for 40 we form. 80. This is for 80. Right. So like this, you can make whatever of your interest. You can play. That's what. Literally, you can play with every point. You could see here 20. It is forming within short span of time. 40 will take more time. All how much time it takes also you can calculate. How much time it takes for your for a depth of 40 mm, you can say. That's the beauty of all these things, right? For 60 mm, for 80 mm, everything will keep forming. You can see on the screen 4 different formations with the different depths and all, how it forms. Of course, for present, this is 1 year work. It will take 1 year for a student to start from scratch, practice, get acquainted to all these input details, solution, post-processing, taking results, recording. Every step will be a hurdle. It's not that easy for a student to start with and complete. It looks very interesting to see, to watch, but when performing, it will be painstaking. So that's what I told you. Should have patience to sit with the system and passion for that particular subject. Then you can enjoy. Right. So this is how we will get all the components of various depth, how it forms initially and then intermediate and then final. For 40 mm, for 60 mm, for 80 mm. Sir, you think of, if I have to manufacture this, how much time it will take, how much cost it will take, how many mistakes. If any mistake I make on this computer, no issues, no problem. Just erase and start doing once again. Maybe time is wasted. That's what. But if it is experimentally, if I have to do, cost involved is very, 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 very much high. And then you can, that's how you can extract same different what do you call, results, and you can compare and see all those things, how I can manufacture this. Yeah, you could see how I have manufactured this. I will put every one biscuit inside so that my depth will change, and then gas comes inside it through this hole and goes out of this hole, right, and forms. It forms, literally it forms, right? And then this is how you will manufacture. Depth of form is 20, depth of form is 40, 60 and 80. It goes. You see, initially you will get for 20 and 40 complete formation, whereas here it gets punctured. You may not go beyond certain depth. So that and all will become its limitation of the process or limitation of the material. It is a very slow process actually, right? So this is how, then you have to cut it, because you have to check for the thickness distribution. Then you have to, cutting is a challenge. It's not that easy. Whereas you will get the thickness curves in FE very easily, right? Then you have to measure and then you compare the results. So similarly, I have one more theoretical analysis for how it is a single stage, double stage and all. You just have a cylindrical die, you apply pressure, you will form it over here. If it is with many curves like this, if I apply, what happens? And then you could see whatever I have manufactured, I can still make the depth. That's what I told you over here. See, if you take 80 mm depth, it's not forming completely. So this is a challenge. I want 80 mm depth. So then how I can manufacture? Then I have to go with what? I have changed my style. So now I will use this only for 20 mm, and then I will increase its depth of form using upward pushing. You could see this blue line. Here pressure is applied down. Here pressure is applied down. And then I can apply what? From the top, right, sir? So then you have to choose what? Chemical same way, material properties you have to select. You could see the chart. Why I am showing this chart every time for this set of people is, see, students, it is like understanding the process. Whatever you do, if you go to any house, what you can see one reading room, you can see one hall, you can see one kitchen, you can see one bedroom, and then restroom. So this is what same way any software of similar FE tool will have the same fashion. Environment may be different, colors may be different, right? But actually if you go inside, the the theme will be as it is same. So you have to define the model, apply geometric properties, define the model properties, contact bodies definition, interaction data. If you have friction, that's what interaction data, and then boundary condition definition, how you apply the load, that you have to say, and say solve, and then get the results, and then what, present the results or stop the results. This is the ultimate aim of any FEA. Lot of max is involved. That max is what is converted into a software tool. So that for all those things, so like today people will say IoT, ML, data science, whatever it is, all are tools. Core is mechanical, automobile, civil, electrical, electronics. With all this core, whatever sophistication you make for time reduction, for cost cutting, so then we can use such kind of tools. Core will be core only. Core will be core only. If there is no forming, what is the use of FE tool, right? So one should understand that. So be attached with core, then you can enjoy all these things. So that's why I told you, from top I will apply, and then from bottom I will apply. Anyhow, this videos won't play, I believe. I don't know if it, so some mistake has been made. Right. Okay. So this you can simulate the same way, and you could find all this for different cases, and you could get the results. So this is all are sheet forming, right? All are what? Sheet forming. Now I want to go for channel forming, whereas in all these cases, mine is a sheet. Raw material will be what? A sheet, raw material, and then I will apply force over here, and then the sheet gets formed into this shape. The sheet gets formed into this shape. So now I want to go into what do you call how my channel is formed. How my in a channel, how bulk forming. This is, you should know, forging, extrusion, all this comes under bulk forming, right? Sheet metal forming is another area, right? So first is sheet forming we discussed, because majority of the automotive industries enjoys the sheet forming, right? And it requires what? Bulk forming also for that case, right? So we go into equal channel angular pressing. We will see what is this equal channel first. I don't know whether I have kept some, okay, direct simulation, right? Okay, see, yeah, I have a material like this, I have a raw material like this, and I want to put the raw material over here, and I will press this. It is as simple as extrusion. In extrusion, you reduce the cross section. In this case, I won't even reduce the cross section, but the strength will abnormal increase in strength. Students, the beauty of this process is, see, as long as this particular raw material is over here, things are different. As it passes this particular constrained path, things are, say for example, this is MSET exam. Before passing MSET exam, how you are. After passing ESET exam, how you are. So that's the level of change you will get it in this particular material. This will be a raw material. You apply over here, because you see it's constrained more. 135, 120, I have made it for 90 also. 90. See, it comes here and it goes here. Do you think it will be that easy, the raw material? If you push in a press, keep it over here, push in a press. Do you think that easily it will come? Lot of pain will be there. It shears and it forms and comes out, so that every grain size is reduced, so that the strength increases, stiffness increases. So that's the beauty of bending equation. M by I is equal to F by Y is equal to E by R. So first two will also be satisfied, 1 and 3 will also be satisfied. That's the beauty of this particular strength and stiffness. Both will be increased when it comes out of this, right? The more 135, it's almost easy. 120, okay, bit difficult, but 90, it is really a challenging do or die. Either the die will break, or else the press can't push. So it will be very difficult for us to execute it in real life, right? So this is what, so you know what is severe plastic deformation and ECAP and all I have shown you. It's a typical SPD process, right? So this is how we have this raw material. And now I have to select my material properties. For academic research, always aluminum is used because damn easy to process. Aluminum is a beautiful alloy. It is damn easy to process. Right. So you have the die material, which is die steel normally, and you know how to machine this die steel. So then, see, once again, you could see, this is in ABAQUS actually. This is almost the previous 3 case studies or in MSc mark, because it's a flat sheet. That's also an FEA tool. This is also an FEA tool. Everything is FE based only. Names are different. That's it. Okay, you define the process, you define the contacts, you define material, and for this I have to write a subroutine sometimes, then define the workpiece geometry, define the tool geometry. Tool is my punch in this case, and then I have to give an input file and then simulate it, whether it is explicit or implicit. It's all based on the, that's how, see, this FE concept cannot be dumped overnight. Slowly, we learn in bits and pieces, right? One fine day, 1,000-mile journey starts with a footstep. One fine day you start playing with a computer, then you will come to know, yeah, I'm also a program, I'm also what do you call, CAE engineer, not a mere programmer, CAE engineer, right? So lot of job opportunities for this particular, if once you are very strong in FE, meshing itself will give you, there are, so if you go around this what do you call, to this best part of Hyderabad high-tech city, there you can see number of CAE engineers who talk on tea stalls about meshing, mesh tools, all those things, right? So a lot of job opportunities are there. Only thing, you have to gain confidence. You have to gain confidence, right? And you should mastery over it. If you start at an early stage, like first year, second year of your degree, it will be very interesting, right? And today sources are there everywhere in the, what do you call, YouTube is there, open source are there. You can learn whatever you want, right? So I used to do this software like we used to do this like this. You have 135 and this is 120, and I will increase the friction coefficient with 0.1 and 0.2 different oils we use, right? So those parameters of those oils, right, we apply. And then the ram velocity, how the ram comes and presses this, you could see. Same, I have to read once again the same story of how it happens. Right, it's a 3D analysis. Almost all my analysis are 3D analysis. You could see how the strain rate varies. If I apply pressure, how the displacement changes. You see the shape of that particular component which is coming out. It is, the input is a square, whereas the output is a trapezium. You could see it changes its shape, and the same shape you could see after experimentation also. And you see after crossing, it's, or else during crossing, here it may be less. The channel angle is 135. Ram velocity is 0.25 meter per second. Very slowly it's being pushed, right? And mu is 0.1, right? How this particular strain vary, displacement varies, strain varies, all these things you could learn, right? Next is, if it is 135 degrees, how it varies. 135 degrees, how the strain rate varies. for different materials. You simply change the material, you will get lot of information. So that's the beauty of FE tool. Whereas conducting it on experimental setup on floor will be a very challenging task, right? So then you could tap the results, how the viscosity varies, right? If you increase the temperature, it's not that easy. If you increase the temperature and push, right, what happens? At room temperature, if you push, what happens? Several questions can be answered with FEA. Several questions can be answered with FEA. You could see over here, we have manufactured these dies, right? And then if you press it and if you push it, you see how it is coming. You could see over here, it will be a trapezium. Many of the time it cracks. That's what I told. It's not a very easy job in experimentation, right? And we will see how the temperature is. There will be a different type of increase in and then how its microstructure varies. See, before entry, its microstructure will be different. After coming out of that particular what do you call angle, it will be different. That will be something. Okay, so this is another case study of FEA. Students, what you are seeing, this particular FE analysis in a normal laptop of a student will take around 28 to 30 hours to execute. Don't think the result what you are seeing in 2 minutes or 3 minutes. For solving this will take, that to a subroutine problem, for every matrix it has to execute, it will take 30 hours minimum to execute one simulation run. 30 hours. Think of how much heat your laptop will be. So sometimes it crashes also. Laptops crashes for our students, and we will be in dark, how to do, what to do, what not to do, and all. Hence it is really a challenging job one student has to take up and enjoy, right? So that's why nowadays we are doing one analysis. I have not kept over here, maybe it is there or no, I don't know, which is now in progress. I have did for what do you call, what happens, mesh analysis also we have did, what happens, right? So this goes like this. Next is for finite element analysis and experimental validation of a moving heat source in welding. People will say welding, hey, what is there? We see only roadside welding. But if you have seen rocket welding, then you might have, you have seen aeroplane welding. If you have seen ship welding, then you will understand the challenge of welding. We have always seen gate welding or windows welding on roadsides, right? Or else in a, what do you call, razor used for shaving, the blade is welded to the plastic handle. That's really a challenging job. So that's how it's very beautiful to have all these things, right? So I know what is welding, what are the basics of welding. See, it's a very simple job, how to move a heat source on a flat plate. As simple as it is. If I say it, it looks very easy. But go and sit on the system, then you will come to know what is this I am doing. That's the type of pressure a student will feel. But if he has passion and patience, yeah, you could see the results of this particular work. Yeah, okay. So you have different types of welding, where and all it is used. You could see, and you have to select. And then as natural as it is, lot of theory will be available. You have to do some calculations, right? You can consider your heat source in the form of circular disk. You can consider it is in the form of elliptic hemispherical power source. You could see, or else you could consider it is ellipsoidal power source, right? Or else you could consider it as double ellipsoid power source. So 4 different theories are available in what literature. So based on that, you do calculations. I will wind up all these things, right? So it goes, you can see, you do some calculations and you end up with. So that is analytical part. Naturally, no, if you know E is equal to MC square, substitute in that. V is equal to U plus AT, substitute your input values for time T is equal to 1 to T is equal to 100 and have results on your hand. That's as easy as possible, right? Next, you have to go for computer. You see how many things are there to deal with if it is welding. Welding is actually a multiphysics phenomena. You can't say welding is as simple as it is. If you go into that, you could see lot of structural mechanics, you could see lot of heat transfer, you could see lot of initial conditions, boundary conditions, microstructures, metallurgy, what not, physics, surface tension, fluid flow, everything will be there. And if you want to convert all these things, it's not differential equation, you require partial differential equations. And then you have to apply your boundary conditions. You should see graphics, outcomes, algorithms. So all this are required for solving any computational mechanics problem. For this, I used COMSOL, which is a multiphysics software where the supplier is from Bangalore. Yes? Anything? Anything wrong? Hello? Someone's mic is on, I believe. Right. Okay. Fine. So then you have like this assumptions. And then with this, yeah, you could see once again, for any FEA, this is what, no, I have to give global definitions called as input parameters, local definitions called defining variables, geometry, modeling the component, add material, selecting the material, add physics. For me now only it is heat transfer. And then I will go for meshing. And then my study is time dependent study because it keeps on moving with respect to that. And then I will take results. So that's what. Right. So this is for COMSOL multiphysics simulation. This is one beautiful FE analysis, right? Student, this is how I will. You might be knowing, you know how to weld a flat plate. Many of you students, right? Then if you know how to draft it in an AutoCAD, you can do it. You know, SolidWorks, you could model all these things. And then you can feel, yeah, I have made it, right? So then I have to give all the input parameters, but basically I should have domain knowledge of what is welding, what is current, what is voltage, what is I square R, right? All those things. Later you can deal with the type of heat source and all. That may be higher level, but I should know first basics. If I increase current, what happens? If I increase voltage, what happens? What happens to my power? What is my transformer efficiency? Why a new machine's welding is something different from an old machine's welding? Machine, not man, I'm talking about, right? So then all those things, and then you will mesh this. This is what called your FE model, whereas that is only a solid model. Now you have converted it to FE model. You could see what is the maximum element size, what is the minimum element size, how many different types of elements I have used for meshing this. All this are at level high, right? And then I will use a circular heat source, and then I will start supplying the heat. It moves. How my temperature will flow, you are seeing in the right hand side. How the temperature gets dissipates. How the temperature gets dissipates. So that you could see in frame wise, in slice wise, on the surface, in cross section, different cross sections you can view. This is the beauty of any FE software. This you can't see while doing welding. And these temperature will match very nicely with my experimental temperatures. Right. Whereas that you won't get in what the previous case, what you have seen. And then you can find the temperature at this point, at 1/0 point, at 1/4, at 1/2, at 3/4, and at what? At the end of that, how it varies. At different stages I can see, and for different places, for a different time, how the temperature varies. All these things we could see. So that's the beauty. Whereas in different cross sections, you can see in different cross section, you can see in this cross section how temperature varies. You can see in this cross section how temperature varies. Take a biscuit packet of like this and see in every biscuit what the taste will be. And if you take a biscuit packet like this, you can see how it varies. And then what on the surface, how it varies, temperatures. So you can enjoy. That's the power of FE. That's what I told you. You see how the temperature varies at every point in this cross section, you could see. Right. How it varies this side and that side. Yeah. You could see in this case, okay, how it varies. In this case, how a distance varies, temperature, time versus temperature for given time. As you keep on increasing the time, you see heat comes down at particular point, right? So 1 mm, what happens? Everything, when it is at that particular point, heat will be more, and then as it starts moving, heat starts reducing. So it goes on like this, right? So you can see how on the surface how it varies, on the surface how it varies, right? This is with a hemispherical heat source. Provided you see the heat source, this input differs with the formula. This input differs with the formula. You take up a hemisphere, you take up an ellipsoid, ellipse, then x square by a square plus y square by b square is equal to 1 will be given as input, and then it is formulated. If it is circular heat source, x square plus y square is equal to r square will be given. So that's how we solve all these things. If it is an ellipsoidal heat source, you could see how there you may see a pura everything is same like that. No, it's not. Lot of differences. If you start analyzing the graphs, you can be shown. And then you could see for a double ellipsoid heat source, for a double ellipsoid heat source. Oh, let's wait for a minute because my computer is now showing its real colors. So this is a double ellipsoid heat source. This is considered to be one of the better prediction compared to all the other four. We have circular heat source, we have ellipsoid, double ellipsoid. With all those things, only this double ellipsoid gives a better prediction, either in analytical form or experimental form, or else in what simulation form. We could see all those things. So I have did it on a flat plate. So now I told my student, let us enjoy the same phenomena on what circular coordinates. We tried for a solid pipe, solid, not pipe, solid rod, right? Pipe is different. You have then you could see how the temperature varies, right? So it will be for a what circular heat source going on a solid pipe, solid rod. You could see here how the heat varies, how the heat flow varies. You could see. Okay, so it goes on like this, students. So that can you able to see this, how the heat flow as the heat source comes here, how it varies here, and how the heat reduction takes place in its initial with respect to time. So all those degrees centigrades, everything can be analyzed. Everything can be analyzed, right? Yeah, my computer is moving slowly now. Yeah, this is for a hemispherical heat source. Yeah, next is, you can see the same similar phenomena will be there, but it's not same process, but you have to sit and execute. It says, I will, after 7 hours only I can give results. So you have to wait for 7 hours. It will slowly, and then you can take your extractive results. So that's the beauty of this particular FE. All this is for pipes. Then the same work we have did it for what? A hollow pipe. A hollow pipe, temperature variation will be different. For a hollow pipe, temperature variation will be different. Right? Yeah. This is a hollow cylinder. And now you can start seeing how its meshing is, all those things. And same naturally we can, it's an academic exercise. Very nice student get control over the entire software. The fellow, when he started, he can't move the heat source, like he was struggling beyond. Sir, I will drop, sir. That's what was his level of... but still we pushed beyond our limits, and luckily we could strike. Right. So that's the, you could see how heat varies, how the temperature variation is. It's not as it is in the same... The temperature, because inside is also hollow, so you have more surface area, the temperature will be different, right? So you could see all these things, and you have extra graphs for this case. Same case. Yeah, it may not be it may be difficult for a student to grasp all these things when dumped in 1.5 hours. It may be very difficult, but it may give you a thought, why not I? So if that thought comes, yes, this lecture is useful to you, right? So how those on surface, how it varies. So that I could do for a hemispherical. This is one of the beautiful where double ellipsoid will be my good heat source. Double ellipsoid out of 4: circular, hemispherical, ellipsoid, and double ellipsoid. What is the better rated heat sources? A double ellipsoid heat source. If you see into the formulation of welding by R.S. Palmer, you can celebrate all these things, right? Yeah, this is double ellipsoid. You can see all. Then it is being attempted for a hollow sphere also. Hollow sphere, 4 materials, 4 different types of heat source. So if at all I have to make this, it will be really an challenging job. Challenging job. Double ellipsoid. Yeah, you can have a look of this, how the heat varies inside a hollow sphere. Hollow sphere. You know, making of a hollow sphere is very difficult, students. It may be very easy on screen, but if I want to make a hollow sphere in real life, what do you call, made of metal, you want to make a hollow sphere like a coconut. So it will be really difficult for you to manufacture. You can attempt to make an hollow sphere. You can attempt to make an hollow sphere. Then you will come to know the interesting part of this, how much challenging it is to make a hollow sphere and then weld it, right? So now the system is moving slowly because lot of videos are imbibed into this PowerPoint. So naturally it will suffer. Of course, I am at the verge of my maybe 10 slides more, and I have not kept my ongoing project of compaction, powder compaction, which is also did by FE with my students in ABAQUS only. It's in ABAQUS. Students are doing very good with that. Yeah. And then you see how it varies. Type of specimen at 1/4 length for different locations, how this particular temperature varies. And then you have to go and do this on the same flat plate, on the same solid rod, hollow rod, and this very interesting hollow sphere. May not be exactly hollow sphere, students. And then we use welding, temperature, infrared guns and all to measure. Of course, it's not the right methodology. So almost like a hollow sphere. Almost like a hollow sphere. All this work done in the challenging pandemic situation times. Right. So you could see how we have recorded the temperature. You could see this particular weld is flat piece weld is shown, and I am taking 1045 out of that. Right. With solid proofs. And then you can type of heat source. You could see the theoretical results. You could see the numerical results, and you could see experiment results. And you could see I am very near, almost near, for in certain cases at least, right? That's the beauty of FE. Numerical results are nothing but FE results, and this is how we go with temperatures, all those things. Yeah, with this I thank what do you call, this is FE is really a very interesting tool if once you know the basics of FE and you have patience to sit on computer and then you start practicing FE. Down the line of 5 years, you will become an expert. You will be called by someone to share your thoughts, with youngsters so that they get ignited. Brains get ignited, motivated, all those things, and take up FE as their core job. Very enormous amount of jobs. Plenty of jobs are available for CA engineers, right? And I sincerely, the acknowledgements, this entire lecture is not mine absolutely. I'm just only what you call nimittam matrame. That's what I can say. I sincerely acknowledge my gurus who had made me with less flaws, and teachers who have taught me the basics, my UG students who teach me day in and day out the basics, my PG scholars who teach me very big concepts by their very silly questions, so called silly questions, will open a door for some PhD research works. And I sincerely thank the automobile engineering department for giving me an opportunity to share my thoughts and little work what I have done, and to the organizers of finite innovative methods in finite element analysis using analysis and ABAQUS, and Department of Mechanical Engineering and head of the Department Mechanical Engineering, MVSREC, for giving me an opportunity to share my thoughts. Any questions students can ask? Interact. You can interact.
No question, sir.
There are no questions. There are two different understanding. One is left extreme, another one is right extreme. Everything is understood, but nothing is understood. Nice. Anyhow, I thank you, Vijay, for a wonderful opportunity. Thank you very much. Thank you, sir. Thank you very much.